Today we start chapter 16, reaction rates. Uh, if you look at the size of the packet, you can tell there isn't too much to this chapter, so hopefully it goes well for you. Reaction rates. When we talk about a rate, it's the measure of the speed of any change that occurs within an interval of time. So rate is simply a measure of change. If we have atoms of sodium metal, and we showed this earlier in the year in a YouTube video, and they will react with molecules of chlorine. It's an exothermic reaction. It releases lots of energy, and it will turn into sodium chloride. So over time, the reactants will turn into products. In order for a reaction to occur, we're going to discuss what's called a collision theory. In the collision theory, atoms, ions, or molecules have to collide in order for a reaction to occur. Not only do they have to collide, but they have to have enough kinetic energy to cause what we call an effective collision. The more collisions, or the more effective the collision, the greater the rate of reaction. In order for a reaction to occur, we need what is called activation energy. It is the minimum amount of energy to bring about a chemical reaction. Think of activation energy as a barrier that reactants must cross to be converted to product. So here in the picture, A wants to get into B's position, but in order to do it, it has to have a little bit of energy to get it over the hump so that it can then turn into products. We have a term called an activated complex, and the activated complex is simply the peak of energy stored within a chemical reaction. So at room temperature, carbon and oxygen do not combine. However, when charcoal is burned, they will cause the reaction to happen. So once we supply the activation energy, the reaction will occur. So if we look at this diagram of an exothermic reaction, we see molecules are going to collide with enough energy to overcome the activation barrier. At the peak, they form an activated complex, and once the reaction occurs, the products are at a lower energy arrangement, a lower potential energy. So now we have to start identifying a potential energy diagram. This one is for an exothermic reaction. Reactants react, products are produced. So this line shows the potential energy of the reactants. This part shows the potential energy of the products. The reactants have to absorb some amount of energy in order for the reaction to start. It could be from a match, from a lighter, from a Bunsen burner, somehow. Then the energy is released, the reaction happens, the burning occurs until we form our products. If you remember from chapter 15, we have a term called delta H. It's the potential energy of the products minus the potential energy of the reactants. It ends up being this part of the curve. So all of this minus this. Leaves us with this. It's products minus reactants. So small minus large, and small minus large will be a negative value. So in an exothermic reaction, delta H is negative. As you can imagine, if we have an endothermic reaction, basically everything is going to be the opposite. The reactants do not have a lot of energy to begin with. They absorb a lot of energy to get to the activated complex. Then some energy is removed or released, and the products are formed. In an endothermic reaction, the energy term is found left of the arrow, so I have to go back for a minute. In an exothermic reaction, the energy term is on the right of the arrow. In an endothermic reaction, delta H is the energy of the products minus the energy of the reactants. In this case, large minus small, and delta H will be positive. So you have to recognize an endothermic reaction diagram. The heat is found left of the arrow, and the sign for delta H for an endothermic reaction is positive. So you have to be able to draw a potential energy diagram basically from scratch. So on the next page, let's draw an exothermic reaction potential energy diagram. Try and use up most of the page. We have an axis. We have on the x-axis the reaction progressing. On the y-axis, we have the potential energy of the system. In an exothermic reaction, the reactants have a lot of energy. They absorb a little bit of activation energy. The reaction occurs, releasing lots of energy, and then the products are formed. So we have to recognize that this part of the curve is the potential energy of the reactants. On the right, we have the potential energy of the products. The activation energy. We draw these dashed lines just kind of for a reference point. Is the energy to get us to the top of the barrier. At the top, we have all of the energy stored within the system. This is the activated complex. And the difference, so we're going to draw a dashed line here at the reactants, a dashed line to show the products, and the difference between the two is delta H. This reaction is written as something like A plus B makes C, our products, plus energy. Energy is a product, it's given off. And we have to recognize that delta H for an exothermic reaction is negative. All we're going to do now is, it's our last thing, the potential energy diagram for an endothermic reaction. If you want to, you can pause the video and do it yourself first and then check. or just go along with me. We have our axes. The X is the reaction progressing. The Y is the potential energy of the system. Endothermic reactions absorb energy. So the reactants don't have a lot of energy to start with. They absorb a lot of activation energy to reach the activated complex. And then a little bit of energy is given off as it forms the product. We can put our dashes in to help us with the reference. But it's labeled pretty much the same. Potential energy of reactants. Potential energy of the products. A lot of activation energy. The activated complex represents the total energy of the system. And the only thing we haven't done is the difference between the potential energy of the products and the potential energy of the reactants, which is known as delta H. This reaction is written as A plus B plus energy will make C, or delta H is positive. And that is it. Anything else we're going to do, we're going to show in class. So nice job sticking with me. That was about 12 and a half minutes. And we will see you in class.